Okay, good evening, everybody. Welcome to another Cosmos from Your Couch episode brought to you by the Dunlap Institute at the University of Toronto. My name is Michael Reed, and I'm the Public Outreach Coordinator for the Dunlap Institute, as well as a professor of astronomy. And today we're going to be doing something a little bit different from what we've done in our recent streams. So if you've been following our Cosmos from the Couch series, you'll know that we've been giving public talks a couple of times a week for the last few weeks. And we know that one of the things that people enjoy most about these is the chance to actually get to talk to some of the astronomers. And we always run out of time for questions. So we thought today we will turn things over entirely to questions. So what we're going to do tonight is I'm going to introduce you to three amazing astronomers, and then we've solicited some questions beforehand on social media and email, and we'll answer some of those. But we're also really hoping that you'll engage with us in the chat on YouTube tonight and give us any questions you have about any aspect of astronomy. We can't guarantee we'll be able to answer all of them, but we're going to do our best. So I'd like to start by introducing my three amazing colleagues, Dr. Maria Draut, Dr. Abigail Kreitz, and Dr. Katie Brevik. And I'm going to ask each of them to say a little bit more about themselves and tell us a little bit about what each of them does. That'll give you a sense of what we can ask questions about. So maybe Maria, if you'd like to go first.
Yeah, sure thing. So as Mike said, my name is Maria Draut, and I am a professor at the University of Toronto in the Department of Astronomy and Astrophysics. And what do I do? So I am mostly an observer. So I use a lot of different telescopes, both satellites in orbit around Earth and large and small telescopes scattered across the globe. And the type of science I'm interested in is how large, massive stars live out their lives and then eventually die as supernova and other types of explosions. So I do this both by actually searching the sky night after night to look for new explosions that go off, but also by studying stars that are a little bit closer to home in the Milky Way galaxy and nearby galaxies. So that's sort of the 30-second summary.
Great, thank you. Abby, would you like to go next?
Yes, I'm Abby, and I am an instruments builder. So I build instruments to study some of the oldest and faintest galaxies in our universe. And I also study something called the cosmic microwave background radiation. So this was the first light emitted in the universe over 13 billion years ago, right after the Big Bang. And one of the things these two kinds of radiation I study have in common is that they're very faint and very difficult to measure. So my job as a scientist with my colleagues is to build instruments that allow us to probe this faint radiation that are very specialized. They're similar in concept to the cameras we have in our phones, but in reality, they're very large and they take years to build in our labs. Yeah.
Great, thank you. Katie.
Okay, I'm Katie. I'm a postdoc at the Canadian Institute for Theoretical Astrophysics, which is on the University of Toronto St. George campus. I am a theorist, which means that I mostly use pens and papers and computers. And I'm interested in similar types of things to what Maria is interested in. And my main excited focus is actually pairs of stars. So I like to simulate how pairs of stars, which we call binary stars, are born and live their lives together. And I'm especially interested in how, when they interact with each other, this affects their end products of things like white dwarfs, neutron stars, and black holes. And the thing that I do with this eventually is I will use gravitational wave observations with a space-based gravitational wave detector called LISA that will launch in about 15 years.
Okay, great, thank you. So lots and lots of different topics there. We've got everything from the early universe to how do you make new telescopes, black holes, how stars die, all sorts of things. So hopefully people will be interested in asking questions about those topics. To kind of get things rolling, I want to ask each of our speakers to tell us what's the most exciting thing that you've worked on recently. So maybe we'll go with Abby first this time.
Okay, so for me, it's pretty practical. So as I said, I build these telescope cameras. And when we finally finish building the cameras in the lab, we actually take them to telescopes and install them and use them to observe the sky. So about a year ago, I went to a mountain called Kitt Peak, which is in Arizona, with one of the cameras that I'd been building with a bunch of graduate students, postdocs, and faculty. And we actually installed this camera and started our observations. And this was something called an engineering run. So it was the first time we ever installed the camera on the sky, and we observed things that we already know what they look like Jupiter, for example, to see how our camera's working and make measurements that will allow us to kind of further down the line measure these really faint galaxies.
Wonderful. Maybe Maria now.
Cool. Yeah. So I was trying to think about this. Mike told us he was going to ask this, and I still think it was a few years ago now, but still the most exciting thing I've been involved in recently was back in 2017 when I was involved in probably what was one of the wildest rides that observational astronomers have been on in a while. So I was involved in detecting the first light that had ever been seen from a source that also emitted gravitational waves that were detected here on Earth. So I'll back up 2 steps. Katie already mentioned gravitational waves, but LIGO and Virgo are 2 very large physics experiments that exist here on Earth and detect gravitational waves from space. So basically space wiggling when very heavy, massive things spin and move around each other. So LIGO first detected gravitational waves back in 2015, but they detected 2 black holes merging in space, which is awesome. Katie is super jazzed by that. I'm also jazzed by that, but it's harder when I'm an observer because I would love to have something that you actually see light from. And when 2 black holes merge, you don't see light. Whereas it'd be really cool if we could, because both you learn a lot of physics if you have both light and gravitational waves from the same thing, but also as someone who studies explosions, you can actually learn what types of things cause what types of explosions. So usually when an explosion goes off in space, we have to do our best sleuthing to figure out just by looking at the light what it was that actually exploded. But if you also have gravitational waves, then that will tell you what it was, and you can learn things about what actually causes explosions in the universe. So back in 2017, LIGO detected not a black hole merger, but something known as the merger of 2 neutron stars for the first time. And we knew that that could cause light that we'd be able to see with our telescopes. So it created this huge race because LIGO only tells you where something is to a patch on the sky of like 150 full moons. So all of us had, a few hours during the day to really start searching to try and find this new type of explosion. But it turns out we were able to find it in about 15 minutes, as it turns out. And by studying the light from that, we were able to learn things about like where the heaviest elements in the universe come from. But it's still just one of the most crazy experiences because of the whole chase aspect of it.
Great, thank you. Katie.
So one thing that I've been thinking a lot about recently is actually not gravitational waves at all, but it's actually ways to find black holes that are lurking, as Maria pointed out, very quietly. They're not emitting light, but if they are orbiting pairs, like orbiting in a pair with a bright star, it actually makes the star wiggle on the sky. And we have a fantastic telescope called Gaia that is literally designed to just look at the entire sky and figure out where the positions of all the stars that it can see, what they're doing. And it turns out that this telescope is perfect at showing us little wiggles of bright stars that are orbiting nothing. And if a bright star is orbiting, it's got to be orbiting something. And if it's not emitting light, one of the best candidates for that is black holes. And so we've been thinking a lot about how we can find black holes in this way. And there have been a couple of candidates over the past year. One that's way down at the low mass end, that's like maybe 3 times the mass of our sun. And one that was potentially all the way up at the very high mass end, something like 70 times the mass of our sun. So there's a lot of excitement about finding these sort of like dark lurking black holes that are orbiting bright stars.
Okay, wonderful. Thank you very much. So hopefully that gives everyone watching an idea of what our speakers are working on and the whole exciting different range of things going on in astronomy. We're getting lots of great questions. I'm going to try and keep things balanced for our different speakers. I think the first question I will direct to Abby. So this comes from Jessica, whose son, age 9, wants to know what exactly caused the Big Bang.
That's a great question. And the answer is we don't know. So that's actually the answer to a lot of questions, I think, in astronomy, and especially when it comes to the very, very early universe. So we understand a lot of things about the Big Bang and what happened afterwards, but we don't know what started it. And we don't even really understand the fractions of a second right after the Big Bang. And so one of the things that we're actually trying to do with our measurements of the cosmic microwave background are push back as far as we can and get closer and closer to the Big Bang in terms of time, and measure the physics as close to the Big Bang as we can. So we're probably not going to find out how it started, though, I mean, you never know. That's what new scientists are for. But one of the things we can do with the cosmic microwave background is we can actually see signals from the very, very, very tiny fractions of a second after the Big Bang that have made changes to that cosmic microwave background radiation, and try to understand exactly how our universe first began. And one of the things that we think happened is that the universe expanded at an incredibly, incredibly rapid rate right after the Big Bang. And that's why our universe is so smooth and as large as we see it today.
Okay, wonderful. So we don't know exactly how it began, but we know almost back to the very beginning. Okay, so I think this next one may be a question for Katie. And the question is, it's from Gord, if the lasers measuring gravitational waves are so sensitive, how do they stabilize them enough to filter out all the movement on Earth?
That is a fantastic question, and it is really flippin' hard. Basically, the detectors that detect gravitational waves are no small feat. They are the result of millions of dollars of investment and literal decades of people figuring out how to isolate the lasers and the apparatus enough. It turns out the biggest noise source is actually the Earth physically shaking. So the LIGO detectors can tell if there are earthquakes happening all across the United States because they are so sensitive. So the short answer to this is engineers and folks who build detectors like Abby work for decades to figure out how to just beat down all of the noise that they can. And they get really, really creative, and they are extremely, extremely careful. And theorists like myself are extremely grateful to them for doing that work.
Can I tell a funny story about this?
Of course.
So I, at some point a few years ago, went on a tour of one of the LIGO instruments. I think it was LIGO Hanford. And on the tour, we were just walking through the control room, and they have different posters describing different research people have done. It was clearly a poster that somebody had put together after their summer research project. And the project was try to figure out what is the source of this bit of noise. Like, we see this noise, it's there all the time, but we don't know what's causing it. And their project was to figure it out. And it turned out the solution that they came to at the end of the summer is it was actually the speed bump down the road. And whenever a truck drove over the speed bump, it created noise in the detector. And so as a result of this, they removed the speed bump. And that was something that actually happened. I have a picture somewhere of the poster.
It looks like people froze just a little bit there. I apologize if anyone on the stream saw us disconnect. It seemed like people were frozen just for a second, but okay, great. So we have a bunch more questions. I'm going to give this one, I think, to Maria. And this is, how long does it take for a star to explode?
Oh, that's a really good question. There's a lot sort of packed in there. So for a star to actually explode, so the process of, if you take a star, it's at least 10 times bigger than our own sun. At the end of its life, it's going to collapse down on itself and then explode out as a supernova. So the process for the star to actually physically do that, to sort of collapse down and then explode out, you're talking fractions of a second. It happens incredibly quickly. It's a very energetic process. As you can imagine, there's so much energy going into the thing collapsing down and then flying out into space and creating lots of new elements. But it all happens within a fraction of a second. But what's different there, and is a little subtle, you can ask the question, how fast did it actually happen? But then how long can we see it afterwards? And those are two different questions. It turns out that once that explosion happens, you have all of this material that's flying out into space at something like 10% the speed of light, so very quickly. And as it's doing so, it's creating a lot of new elements. And some of those elements are radioactive. And so they slowly decay with time, creating new energy. So the light that I study and see from supernova, it actually will get brighter over a couple of weeks and then start to fade away over months. And you can even see some supernova years later. But that's just because all of these new elements were created that are then undergoing radioactive decay, much like some elements go undergo radioactive decay here on Earth. So the explosion happens in a flash of an eye, but then you can see the light from it for years afterwards.
Wonderful. Okay, so I'm going to skip a little bit in the questions here that people are asking just to try and spread them around equally. This one will be for Abby, and it says, if the universe, or is the universe still expanding? And if so, is there a tangible edge?
Yeah, so this is also a great question. The universe definitely is still expanding. And one of the things that we've actually learned as we've studied our universe as a community, and this is kind of ties into other people's research here, because supernova are actually one of the objects in the universe that we use to figure out that our universe is still expanding. And one of the really cool things is that we actually have discovered that our universe is expanding at an accelerating rate, which means it's expanding faster and faster as time goes on, rather than kind of expanding at a constant rate. So that's really cool. And one of the other things that you asked, which is, do we have an edge? The answer to that is we also don't know that. So that's another thing. We can look as far away as we can possibly see, but we still don't see the edge of the universe. So what's out there beyond is still an unknown to us.
Okay, wonderful. So we've got lots and lots of questions. This one I'll kind of throw to anyone who wants to take it. It's from HK. It says, is there dark matter and dark energy between objects on Earth? You've perplexed our astronomers.
I mean, that's a great question. I would say that part of the problem in answering that question is that we don't know what either dark matter or dark energy are. And so really answering the question of if it exists between objects on Earth might depend a little bit what it is. But certainly for dark matter at this point, our current understanding of it is that it is spread fairly evenly throughout the galaxy. So we know for sure that the Milky Way is sitting in this large, we call it a halo of dark matter. We can tell that from looking at the effects of gravity and how that influences things throughout the galaxy. So our current understanding is that there should be dark matter everywhere. And so that would mean there should be some that's sort of in the area right around Earth. But it's very hard to answer that question without knowing for sure what either dark matter or dark energy actually is.
Anyone else want to jump in on that?
Well, I guess the same thing can kind of be said about dark energy, that depending on what it is, that may or may not be true. One of the ways we think about it now is that this kind of blows my mind, and like this is my field, but if you have just empty space, there's dark energy is like the property that's causing that space to expand, whatever it is. So if it is that, then yeah, it's everywhere. And that's kind of one of the most amazing things about the discovery that our universe is accelerating, is that, how can this be?
Great. So our next question comes from Lucy, age 8, and maybe we can start with Abby and then the others can jump in as they see fit. So the question is, how many different kinds of telescopes are there, and what's your favorite constellation?
Ooh, okay. So there's a lot of different kinds of telescopes, and this actually is really exciting to me because I kind of work on one of the more obscure kinds of telescopes. So the telescopes that you usually think about, there's some like Hubble, so it's in space and it looks at light very similar to the light that our eyes can see. So it's kind of a magnified version of things that our eyes can see. But I work on telescopes that actually are more like radio dishes. So if you look out at a, TV dish or some sort of other dish, that's actually more similar to the kinds of telescopes that I work on. So that's definitely two different kinds of telescopes. And one of the cool things about the kinds of telescopes that I build is that they look like these radio dishes, but then the sensors that we actually use to pick up that light, because it's light that is very different from the light our eyes actually see. They're cryogenically cooled sensors. So that means that the detectors themselves are cooled down to 1/4 degree above absolute zero. So there's a lot of physics and exciting things just going into being able to measure light that's different from the light our eyes see. So there's many, many different kinds of telescopes and much physics and engineering, like Katie mentioned, going into making all of these different kinds of telescopes. And my favorite constellation is Scorpio. And that's because it's harder to find. It's not the most obvious, but I can still find it at night by myself sometimes. So that's my favorite.
Anybody else want to comment?
Yeah, so I'd say that similarly, there's so many types of telescopes, and many of them, as Abby was sort of mentioning, they get divided up a little bit by what type of light they look at. And so we have some telescopes that only detect gamma rays, and some that only detect X-rays, and other ones for visible light, and other for radio. And so that's how many of them get divided up. So Katie and I actually just a few hours ago submitted a proposal to look at things with Chandra, which is an X-ray telescope that's a satellite that's orbiting Earth right now. So there are many, many types of telescopes you can use. And my favorite constellation is probably Delphinius, which is a dolphin. And a similar reason to Abby, it's like not the most common one, but I can still find it. And so it's like my party trick.
Okay, I'm just gonna add my favorite constellation. My favorite constellation is Hercules. And the reason for this is because in Hercules's right armpit, there is a star cluster called a globular cluster where you pack like 1 million stars inside, and it's kind of like Hercules's armpit hair.
Wonderful.
That's so amazing.
Yes. So we've got a bunch of questions all along different lines. So I'm going to throw this one open to anyone. What's a supermoon?
Mike, what's a supermoon?
I was just going to say Mike should answer this.
No, you don't want to take a stab at it? Just going to punt it to me?
Yep.
Okay, so they're punting it to me because this is a tricky question for astronomers. A supermoon is not a concept that astronomers usually recognize. It's kind of a concept that was invented by the media, more or less. The idea is that the moon's orbit is not circular. It's a little bit egg-shaped or elliptical, meaning that sometimes the moon is a little bit closer to the Earth and sometimes it's a little bit farther from the Earth. But the difference is very small. It's like a few percent. So when the moon is closer to the Earth, it appears slightly larger. And when it's farther from the Earth, it appears slightly smaller. And so when the moon is closer to the Earth, people sometimes declare that a supermoon, which is fine. But the problem is that it tends to give people the impression that they're going to be able to go out in the sky and see this as a really obvious effect. But it's sort of about the difference between how big is my fist now and how big is my fist now, right? It's a few percent different. You could notice if you took a photo, but just looking at it with your eye, you wouldn't really notice. So it's not something that astronomers usually get very excited about. But if it encourages you to go out and look at the moon, which is beautiful and amazing and always worth looking at, absolutely. It's worth. If it gets people to talk about the moon, we're happy. Okay, so that's the last question I'm going to answer. This question I'm going to make one of them answer. Even though it's not their subject area. So the question is it possible for a planet to orbit 2 stars?
Yeah.
Go ahead, Katie, yeah.
We know of planets that do this. There are actual planets that are like Tatooine in Star Wars. And it's a really interesting subfield because it actually tells you the conditions where planets and stars form, because this is kind of a weird configuration to think about. And so if you think about planets forming out of a big old disk of dust and gas that's orbiting around the stars it's forming, we now know that you can have planets that orbit around the disk that must be around 2 stars that are orbiting. And so it's a really fun challenge for people who work on theory to try to figure out, like, okay, what are these conditions? How does this affect star formation? How does this affect planet formation? And to truth be told, this is still a pretty unanswered question, but the existence of these planets is very well known. And hopefully in a few years, we'll be able to explain why.
Sorry, I'm muted. There's a bit of a related question that may work as a follow-up to that one, which is, so you've touched on part of it. How do exoplanets form around binary stars? But the other part of this question is, does the binary nature affect their orbit or the definition of the habitable zone around those stars?
Totally. Totally it does. Yeah, so this is like fully an active field of research. Like in complete full disclosure, we just had a like visitor from another institution come give a talk a couple of months ago on research that he's working on now, trying to explain what these types of effects are. There were people working at the University of Toronto who were trying to explain how a pair of stars impacts the types of planets that you can have. We think that you're more likely to have, I think, wider, if you're in a wider orbit, then you're going to be outside of the region where you can have liquid water. So you're going to have things like ice giants. That's definitely something that comes into play when you start having 2 stars instead of 1 star.
Katie, can you tell us what an ice giant is?
Yes, that's a word that maybe sounds made up, but it's basically, this is another word for planets that are gas giants, like the giants in our solar system, like Jupiter and Saturn and Neptune. This is just outside the ring that we could draw, sort of like in a cartoon around a star where ice forms versus having liquid water.
Great. Anyone else want to comment about habitable binary exoplanets?
Yeah, I would say part of something that goes into that too, that Katie touched on a little bit, is that being in a system with binaries or 2 stars, it can affect. So we observe systems like this, we see them and we know that there are planets that are around 2 stars that are orbiting each other, but it could affect the long-term stability of that. So it could be that it's something that we see now in this snapshot, but that, give it a million years and that planet will be flung out and it wouldn't be stable. And that so factors in too, because we know that life took, billion years to form on Earth. And so if it's something that a planet could form there, but maybe it's not a stable situation, then even if it were in some kind of habitable zone, if it can't stay there for very long, then that will affect whether life could actually form there. So that's another thing that gets factored into it. It's just much more complex system.
Wonderful. So this question, maybe we can start with Abby, and then if others want to jump in, they can. So the question is, it's from Vineet, and it says, basically, what is the center of the universe, or is it known at the present?
Yeah, so one of the funny things about the way we explain the Big Bang is that it kind of makes it seem like there is a center of the universe. In all the pictures, you kind of see the universe starting out as this really tiny thing and then expanding faster and faster. And like that kind of gives the impression that there's a center. But kind of a better way to think about it is that the universe was everywhere that we know it and there isn't a center. And then the universe started out super, super dense, and then it expanded at an incredibly rapid rate and now is much, much less dense. So there isn't a center, but what we, when we look out, what, it looks like we're looking from our center, but basically any observer in the universe would experience the universe in that same way. And it's pretty cool because, there's some bound on the light that we can see. So light has a finite travel speed. So as it's traveling towards us, it takes some time. So we can only see as far as light has had time to travel through the history of the universe, which is basically 13.7 billion years. And that's true of all the observers everywhere in the universe, if there are any. So so there's no real center, but a lot of the ways that we explain the Big Bang kind of makes it seem like there is. But a better way of thinking about it is that, we go from a universe that's super dense to kind of the less dense universe we see today.
Wonderful. So if you're interested in learning more about that, we had a talk a couple of weeks ago in this series about misconceptions about the Big Bang, which dealt with issues about the size and shape and edginess of the universe and center and all that good stuff. Okay, so here are some questions, related questions that anyone can jump in on. The first one is, do all galaxies coalesce around black holes?
That's a super good question. So this is a theme. We don't know for sure. We know that there is a supermassive black hole in the center of our own Milky Way. We know that very well from there are amazing videos you can find if you look on the internet we can actually look at individual stars and watch them orbit around this just seemingly empty space at the center of our galaxy. And so we know that there's a supermassive black hole in the center of the Milky Way. We also, from similar arguments and other types of observations, we know that many other galaxies also have supermassive black holes at the center. But there are one or two cases of galaxies, even just within our own local group, where it's not as clear that there is something in the middle. And similarly, there are lots of different types of galaxies. Some are big spiral galaxies like our Milky Way. Other ones are tiny, dinky little dwarf galaxies that are very irregular in shape. And it's a very open area of research to understand, are there sort of more massive black holes sitting somewhere in those galaxies or not? So I would say we don't know for sure, but there are a couple galaxies that it does seem like maybe they don't, but an awful lot of them do.
Wonderful. And we have a related question, which is, again, anyone jump in on this if you like. Do black holes have a magnetic field?
That's a good question. So one of the reasons that apologies if you can hear motorcycles outside. My street loves motorcycles for some reason. One of the reasons that I love black holes is that they are incredibly simple objects. So when you describe a black hole, you describe it with a mass, you describe it with a spin, so if it's rotating, and in some theories, you describe it with a charge. And so if it has a charge, that charge is going to, because it's spinning, create a magnetic field. So we think that probably black holes do have magnetic fields, and certainly the best simulations of accretion disks around black holes and things like that take into account magnetic fields, but we have not measured a magnetic field from a black hole or anything like that. But incredibly simple objects. Stars have like temperatures and brightnesses and sizes and all this stuff. Black holes have like a mass, they have a charge, and they have a spin. They're awesome and they're simple.
Okay, well, while we have you, Katie, maybe I can give you this one. So given that LIGO has proven the existence of gravity as a wave and not just a field or a particle, are there any other applications that are possible from this knowledge? And the person, Dave, is suggesting something to do with constructive or destructive interference, or maybe anti-gravity equipment or something.
Ooh, good question. So I think, so one thing that I think they were called Dave touched on is the idea of interference of waves. You can absolutely do science with lenses, interference of waves. So one of the things that I actually worked on a year ago is the idea of measuring how dense a star is that's all the way across the galaxy, because it is orbiting something that causes a gravitational wave. And if it eclipses it, the star's gravity has an effect on the gravitational wave. And we can tell how dense the inside of that star is, even though it's all the way across the galaxy. So there are absolutely ways that we can like use gravitational waves as probes of other astrophysics. In terms of doing something like anti-gravity here on Earth, I don't see a lot of prospects for that personally, but I'm also not a particularly imaginative experimentalist. So I, of course, always go straight to the astrophysical things that we can do. Don't let that fade your shine. If you're interested in thinking about that stuff as an experimentalist, please keep thinking about it. But I don't personally have ideas for that.
Okay, wonderful, thank you. So we have a very eager young question asker, Aiden, age 9. We've got a couple of different questions. So remember, Aiden is 9, and we want to try and answer this at the appropriate level. The question is, could someone explain exactly what is a black hole?
That's a hard question, Aiden. So when I actually try to think about what a black hole is, I usually get all frazzled and freak out a little bit, because when you think about it, a black hole is literally like a hole in space. It is, in the simplest terms, it is something that has so much gravity that if you get close enough to it, you're never going to come out. You will fall into that black hole no matter what. Everything that gets close enough to it will fall in. So in a sense, a black hole is just something that is so dense and has so much gravity that nothing can escape it. When I actually think about black holes in the universe, I think of them as bowling balls with a mass and a spin. I just think of them as a thing that exists in the universe, and its gravity affects the things around it. But the real truth is that it is just the most infinitely dense thing that exists in our universe, and it has the strongest gravity that exists in our universe.
Thank you. So another question from Aiden, I think maybe this one for Maria, which is Aiden wants to know what happens if two stars are too close to one another? If they explode, how big would the explosion be?
This is a great question, Aiden. So if two stars are too close to one another, so there's a couple different things that can happen. So first of all, what too close is kind of matters for what type of star you are. So some stars are very big and some stars are very small. And so you have sort of different amounts of how close together you can be or not. But often, and this is a huge part of what Katie actually studies, is if you have two stars in a binary that initially they're fine, but as stars change throughout their lives, some of them will get bigger throughout that process and might actually start to swallow the binary or other star that's around it. And huge work goes in. We call that, we're very creative with names, but so we think of stars as having envelopes. That's like the outer part of the star where most of the hydrogen is called the envelope. And so if a certain star expands throughout its life, kind of like the sun will become a red giant at some point in its life, if a star is in a binary and it starts to swell up and it starts to swallow its companion, we call that common envelope. And it is hugely important for understanding things like neutron star mergers and black hole mergers, but we don't really understand the process. So when one star starts to swallow another, you can either start a runaway process where they actually spin together and merge, or you can start a process where they sort of do that, but then have a mini explosion where they throw out some material and end up surviving afterwards. But that is, we don't really know for sure. There's also a huge question of if you have two stars in a binary close to one another and one of them explodes, what happens to the other star? And it actually totally depends. Sometimes when one star explodes, that other star is going to get flung off into the universe and be moving at incredibly high speeds. We call them runaway stars. So if we are looking for stars zipping across the sky really fast, that could be a star that was in a binary and then got flung out. But we know also sometimes one star can explode and the other one just kind of puffs up a little bit, but just keeps on rocking after that. So there's so many things that can happen. And this is part of why there's sort of a zoo out in the universe. We see so many different types of explosions. There's so many different ways that stars can burp and hiccup, and many of them are related to stars being close together to each other.
So it's a complicated topic, trying to figure out how stars explode and how they merge and why. Yeah, okay. So let's see, lots of different things we can touch on here. So maybe this could be, I think maybe for Maria or for Katie. Ross asks, would a merger between a pulsar and another supermassive object affect its pulse rate right before collision? And maybe for the younger viewers, you can explain what a pulsar is.
That's a super fun question. Okay, so what is a pulsar? Maria talked about neutron stars. We know that neutron stars they're these balls of effectively neutrons. They're super dense. They're the densest things in the universe that exist that aren't black holes. They're roughly like 10 kilometers on a side, and they have extremely strong magnetic fields. And because they have these strong magnetic fields, they actually emit radio light out of the beam of a pulsar. So say this is my pulsar, you can imagine light sticking out and it spins. And so lots of neutron stars have this. And a pulsar is just one where this beam of light, this radio light, crosses our line of sight. So a pulsar, it's kind of like a square rectangle deal where all pulsars are neutron stars, but not all neutron stars are pulsars. So now you imagine that we have a pulsar. We can see the light pulsing at us as this neutron star is whipping around. As it gets close to a supermassive black hole, the gravity gets really, really strong. And because the gravity gets strong, it actually takes the light longer to get to us. So the closer a pulsar gets to a supermassive black hole, we can actually tell that that's happening. If we see a pulsar that its light beams are slowing down, we see pulses and with longer and longer time in between, that would be an indicator that it is literally falling into a supermassive black hole. So that is a thing. We have not seen this yet, but that could be, actually, it's probably pretty unlikely that we will see it, but we can write down theories for what it would look like.
That got me very excited as Katie was describing that. I was thinking, that sounds amazing. Have we seen that? I thought I was about to learn some.
I wish.
That would be amazing. I love that. Okay, lots of good questions here. So Saida says, what are the similarities and differences between black holes and neutron stars? They're both these really dense things. So how are they different? Who wants to jump in?
I can jump in. So they're both these really dense things that we mostly see due to their effects of gravity on other things. So I would say the biggest sort of difference you should solidify in your head is that we still think of neutron stars, because they aren't all the way to black holes, as so two things. They have a surface. So like they have an actual size and a surface that things can land on as opposed to getting sucked into. So they have an actual surface, and they are still made of matter or material. So Katie said it's mostly neutrons that are packed together really tight. Think of almost like the nucleus of an atom, but it's something that's like the size of a city and the mass of our sun. But it still has a surface, and it's still made of matter or material. So that means it can still produce light that we see. So that's one of the big reasons that I talked about this neutron star merger early on, and how we were able to see light from it, whereas we wouldn't if it was the merger of two black holes. And part of that is because when neutron stars start to merge together, because they're still made of matter and actual material and have a surface, they start to get sort of torn and ripped apart. And when they get ripped apart, the actual material that they're made of gets flung out into space, and we see light from that. Whereas black holes are just so dense, you shouldn't think of them as having a surface or really being made of matter anymore at all.
Amazing. Katie, do you want to add anything to that, or you're good?
Maria basically said what I was going to say. The main difference is that neutron stars are actually matter and a surface. A black hole is just a big old hole in space. There is no surface.
I love that description. Okay, so this is a question I think maybe everyone can take a stab at individually. Maybe we can start with Abby. The question is, what's the most exciting theory you're currently following? This comes from Gord.
Yeah, so one of the theories, and this kind of relates to something that I talked about earlier. So one of the exciting theories that we're trying to solve as physicists and astronomers is that this theory called inflation. So inflation is a theory that said fractions of a second after the Big Bang. So like 42 zeros, like like many zeros, and then a number, fractions of a second after the Big Bang. We think that the universe started expanding at an incredibly rapid rate. And then at some point it slowed down, and we don't really know why. And then the universe kind of started expanding in this normal way that it does today. So that's the theory of inflation. And people came up with that theory because one of the confusing things about the universe is that it looks the same, like on average, no matter which direction you look. So if you look out, this way with your telescope, you see like a universe that has kind of the same properties as it does if you looked in the other direction. But the only way this can be explained is if those parts of the universe were kind of in contact with each other at some point in the universe, is history. So inflation was the thing that we came up with to explain why the universe or like why the universe is the same in both directions, or any direction that you look. And one of the hard things about measuring this is that it's very hard to measure things that happen fractions of a second after the Big Bang. In fact, there was no light, so we can't use the traditional things we do, like use telescopes to actually look back and measure that time in the universe. Because like I said earlier, there's this radiation that was emitted 300,000 years after the Big Bang, and that's the first light we can see in the universe. So what we actually do is we actually look at this first light and we look for something that might have affected that light. And one of the things is that if that universe was expanding at this incredibly, incredibly rapid rate, there actually could be bending of space itself that leaves imprints on this light. So it's actually the same gravitational, like not the same ones, but the same concept of the gravitational waves that come from black holes or neutron stars colliding. But there's also, like, when you have this very rapid expansion of the universe, you can actually create gravitational waves as well, but they're much, much, much fainter. So we really look for like tiny hints of signals from them to probe this theory of inflation.
Wonderful. Katie or Maria, do you want to talk about an exciting theory that you're following these days?
Sure. So a theory that I'm trying to follow up on is, so we as observers can look at the sky and try and measure what fraction of stars are single stars like our sun versus binary stars, like we've talked about a couple of times in this chat so far. And when we do that, we find that especially when you consider stars that are very massive, so massive enough that they will eventually explode, we find that essentially all of them are actually in binaries. And essentially all of them are in binaries and close enough that almost all of them are actually going to interact with each other throughout their lives. So sort of like I was describing the mess before, that there's so many ways stars can sort of run into each other. We think that should happen to almost 2/3 of massive stars in the universe. And one of the most common things that our theoretical models say should happen is that you have one star and another star here. And one star slowly starts to expand as it ages. It gets bigger and bigger, but it gets so big it starts to dump material onto the other star and basically have its whole envelope removed. And so at the end, you should end up with a star that is just, as opposed to being made most of hydrogen, it's being made most of helium. And we think that this should happen. Like, we think we're pretty good at understanding our models and our theory. And we think that something like 1 in 3 massive stars should end up like this, where they have basically this helium star in a binary with another one. So yeah, 1 in 3, we think this should happen to. And gosh darn, if we have never been able to find any of these stars. And so if we think it happens to 1 in 3 massive stars, why aren't we seeing them when we look up in the universe in the sky? And it turns out we think it's just because they're hard to actually see, because that star that's made of helium, it's really, really hot. So it emits most of its light out in the very extreme ultraviolet, not invisible light that our eyes and most of our telescopes see. So we're starting, this is something I've been working on for a while now, trying to trace down and see if we can actually find these stars, because we think it should be super, super common and we just haven't seen them. So either our theory is wrong or we haven't been looking in the right way up to now.
Amazing. Katie,
Yeah.
any
Okay.
theories you're interested in?
So because I'm a theorist, I feel a little dirty, like saying that my favorite theories are the ones that I came up with. But I feel like that's the whole point of being a theorist, is coming up with theories and getting excited about them. So the thing that I'm most excited about right now is, as I said, my own theory. This is some work that I've been doing over the past couple of years, and it's to actually take predictions of these massive stars that Maria is talking about and predicting how many black holes there are that exist in our galaxy. And so I have a prediction on the books that says that there are about 1 million black holes in our galaxy. And I have predicted the future telescope, specifically one that's already working, Gaia, in the next 5 years should find hundreds of black holes. So everyone watching, come back in 5 years and tell me if I was right or wrong. But that's the theory that I'm most excited about, is finding these black holes that are lurking. I think there are hundreds of them out there.
Okay, so mark your calendars. April 2nd, 2025, we're going to have Katie back. Katie's going to tell us whether or not there are hundreds of black holes in the galaxy. So there's lots of good questions coming in via the chat. We're going to go until about 8 o'clock, so another 10 minutes or so. And I'm going to do one that we got by email. This is a great question. I don't know who to direct this to, so anyone can jump in if they want. Probably any of you could say something interesting about this. And the question is it possible that there's no mass where we suspect the presence of dark matter, only lasting distortions in space-time caused by something that used to be there? So are we maybe sort of wrong? There isn't really dark matter. There's just the dents left over from stuff that isn't there anymore, has moved on.
That's a really hard question. But it touches on something that's actually really cool about gravitational waves, which is we call it in the field in gravitational waves, we call it memory. And so the idea here is that if you do a really big stretch and a squash of space-time, space is not a perfect elastic. And so if you overstretch an elastic, it's not going to go back to exactly the same shape that it was. And so this is literally space having memory from enormous gravitational waves going by. It turns out I have friends who have predicted theories saying that the future space detector, LISA, the laser interferometer space antenna, should be able to detect this type of thing happening. However, I don't think that this accounts for dark matter. So there's nothing that we have written down yet that suggests that this type of memory could be responsible for the types of things that we see dark matter doing. It certainly doesn't make stars orbit faster in the outskirts of galaxies or anything like that. It's totally different, but you can totally over distort space in such a way that it is just leftover curvature.
That's totally awesome. I did not know that.
We're teaching each other here, it turns out. Okay, wonderful. There's so many great questions coming in. So many. Let's see. Here's a one we can maybe do quickly. Does sound travel the same in space?
I mean, that's a great question. But so I would say yes, sound travels the same in the sense that sound doesn't behave differently, but part of what matters for how sound moves throughout space is how much material you have between you and where the origin of the sound was. It's actually literally like a pressure wave moving through like I guess the room that you're in now as you're hearing the sound of my voice talking. It's actually like material moving in response to that. So in space is not empty, it's not a vacuum, but there's a lot less material. So the speed of sound would be much different than the speed of sound here on Earth because just the actual physical conditions. So how much material is there, what temperature it's at, all of that is going to affect how fast sound can actually move through space. So that will be different if you're out in space than if you're on Earth, but the physics that defines it is the same. If that makes sense.
Yeah, I think it's interesting that we often say, when people ask this question, we say there's no sound in space. And yet actually, some of what we study is the effects of sound traveling through space. It just depends on how much stuff there is there to travel through.
So the result is that, in essence, you don't really hear anything, but it's not because the physics it's different. It's because there's so little material that can actually like carry the information of the sound to you.
Okay, it's hard to choose. We're getting down to the last few minutes, but we have one from Susan. She says she's here with her 13-year-old son, Owen, who would like to know, how can you see a black hole with a telescope? I agree, this seems wrong, doesn't it? They're supposed to be black. Come on.
Totally. So we can see black holes with telescopes because we do not actually see the black hole itself. We are always seeing the effect that black holes have on something else. So either you can see the effect that it has on some other object, like Katie talked about, if it's close to another thing that is orbiting or moving around it, you don't see the black hole, but you see the material around it. Another really common way that we see black holes with telescopes, it's not something orbiting around, although I guess it kind of is, but a lot of black holes that we see in the universe have disks of material around them. Kind of think like Saturn's rings, but even more tighter in. So it's actually like material that is being funneled down onto the black hole. And that material is spinning so fast because the black hole is so dense that it heats up to very hot temperatures. And we're seeing the light and radiation from that really hot material that's orbiting around the black hole as opposed to the black hole itself. So you're always seeing the effects of the black hole on other things when we observe them with telescopes.
Okay, I got two rapid fire questions for you here. They're related, sort of. They're both about how big things are. So Saida asks, how big is Sagittarius A? And somebody else, I've lost track of it, asks, how big is or Vineet, how big is a pulsar relative to Earth? So how big is a pulsar? How big is Sagittarius A? And what is Sagittarius A?
So a pulsar could sit on top of Toronto. It would do a number, it would do some damage if it sat on top of Toronto, but it could physically, it's small enough to do that. They really are something like 30 kilometers across. They're really small. Sagittarius A star is this monster supermassive black hole that's in the center of our galaxy. And it is like 4 million times the mass of our sun. So that's pretty whopping big. You can actually do a conversion to talk about the Schwarzschild radius. I'm going to do this on the fly, and it's probably very dangerous.
Okay, Katie's actually trying to calculate it.
I'm calculating this.
Katie's doing math, everybody.
Watch out. Okay, so you can convert the size of a black hole to the size of its Schwarzschild radius by knowing that one solar mass is 1.5 kilometers. That's just like a thing that I remember from class. And if you do that, it's 6 million kilometers. So that's what the Schwarzschild radius is of the supermassive black hole. That's
so what's a Schwarzschild radius?
The Schwarzschild radius is the ring around a black hole at which no light will escape. So it's kind of like the shadow of the black hole. That's what I think of black holes as being. I think of them being a bowling ball with a radius of a Schwarzschild radius. That's probably not totally correct, and I bet a lot of my friends are cringing, but that's what I think. But it's like that's so small. It's so small if you actually think about it. You take 4 million times the mass of our sun, and you cram it all together, and it's only 6 million kilometers on the side. Like, that's tiny when you actually, I don't know, it's super small. Another fun fact, the size of a black hole that would be the mass of Jupiter is the size of a human. That's another way to think about how tiny black holes actually are. They're really, really small.
Very, very strange objects.
They're super weird.
Okay, well, maybe, so there's so many great questions, and, I thank everyone very much for coming. I hope that, you've enjoyed it and that you've had an opportunity to get at least some of your questions answered. There's definitely some we won't be able to get to. Maybe we'll try and hold another one of these question and answer periods so we can get through even more. But just as a kind of closing question for everyone, we'll go for a big idea. And this question comes from Canadian V. Stig, who asks, what are your thoughts on the Fermi paradox? This may take people a minute to decide what their thoughts are. So for those who don't know, the Fermi paradox is this idea that the universe seems to be devoid of life beyond Earth, and yet all of our quickie calculations suggest that it should be possible for alien species that are out there to colonize at least our whole galaxy or the whole universe in relatively short periods of cosmic time, and yet they don't seem to have done that. So why?
My personal view on this, not backed up by like math or anything, like actually working through that we should have propagated the whole universe, but just space is actually really big. Like, it takes a long time to get any information from one place to another. So even if there's time in the age of the universe for life to have moved and populated throughout our entire galaxy, I'm not sure there's time for us to have heard about it within the last, couple millennia of humans being here on Earth. That, like, it doesn't puzzle me or worry me too much that just it's really hard to get information in terms of actual communication in some way between places in anything like a human lifetime. And so that's just my personal view and how I sleep at night. But
yeah, I think I agree with Maria that, we've been observing our universe for a very short period of time. We've been existing for a very short period of time as humans. And yeah, things are super, super far. I mean, the fastest thing in the universe that can move is light, right? So you know, it still takes light 4 years to get from the nearest star, and like to get to another galaxy, you know, it takes an incredibly long time even for the fastest thing in our universe. And yeah, I just think that I agree, like the universe is just so vast. And you know, Katie was talking a little bit about how, you know, that black hole is really small, or our universe is really big, like incomprehensibly big. So I think that that's kind of how I think about it.
I totally agree. We're gonna code 3 for 3 on this. The space is just too big. Like it's just way too big. So I don't know. I don't think it's a negative thing, but I'm not super hype about colonizing the galaxy in general, let alone actually physically trying to do that. Cause it's a big ask out of us as humans. I think we have enough going on here to do good things here on Earth.
Okay, wonderful. Thank you very much, everybody. So we're going to wrap things up there. If you've enjoyed this, please, leave some comments for our speakers in the chat. I'm sure they'd like to hear how you felt about this. And if you have any suggestions for topics for future Couch from Your Cosmos, Cosmos from Your Couch chats, we'd be happy to take those suggestions. We've got loads of astronomers eager to talk to you. So if there are topics that interest you, do let us know and we'll try and schedule those. I see people asking, will we have another question and answer? I think, yeah, this seems to have gone really well. People seem quite keen. So maybe we'll get some of our astronomers back to talk to you again sometime soon. If you're interested in hearing more, follow the Dunlap Institute on social media, and you'll be able to find out about all of our upcoming events, which will be online for the foreseeable future. But once the pandemic hopefully winds down, we'll get back to doing events in person. So thank you very much, everybody. Thank you very much to our astronomers. We can do a round of virtual applause for them. Thank you very much. Have a good night, everybody. Stay safe.
Thanks, Mike.
Thank you.